So we've been looking at these things. We know that current in a wire now will cause a magnetic field. And so I could use a compass, right, to check that out. And so I want to just kind of review this with you and turn this on. What? Sorry. I'm sorry, that moved on me. I don't know why I did that. I can check that out again. So I'm really looking at the compass here. So let me turn it on again. It keeps moving. What's going on there?
Do it again. Hold on. Do it again.
Yeah, it's a magnet, but what's inside the wire? We've already looked at wires, right? What's inside the wire?
Current.
Moving.
Well, right now, is there any current in there?
No.
But what kind of material's inside the wire?
Charge.
Metal. What kind of metal?
Conductive.
Copper. Is copper attracted to magnets?
No.
No, so that can't be it, right?
Hold on. Do it again.
Crazy. It's crazy talk. So anyway, I'm looking here. I don't know what's going on there. Let me. What's going on there? Somebody explain what's going on. I don't understand.
The charges are making a magnetic field by moving
Wait, if it's making a magnetic field, wouldn't it be attracted to the magnet? No.
or repelled. It could. I don't know which.
Well, wait a
pole it
second. Is this a monopole? Can you have magnetic monopoles?
No.
No. So like one of these is probably a north, the other one's a south, right?
Yeah.
Oh, maybe.
Well, they could be attached between something.
Let me turn it on again. Let's watch it
Okay.
again. Well, I don't even need that. I guess this is more interesting. Which way is it moving? That way. Okay, well, let's see if we can explain this behavior. Which way?
Maybe the field is going. The field on one side is moving one way, and the field on the other side of the wire is going the other way. So if those are acting against whatever that magnet's polarity is, then it'll repel on both sides.
Okay.
The polarities on each side of the magnet are different, but they're also different from the magnet side, so they're being pushed away.
Well, let's see if there's a way we can figure out which way it will deflect. Then.
Flip the
How about I flip the wires?
Yeah.
A little bit easier? Okay. Flip the
I
wires.
think that's too difficult.
Oh my god, the red's not in the red.
Blasphemy.
That was gonna explode. Go towards.
So what's the theory?
It will now go into.
Okay, let's see if it's right.
Yeah.
Okay, so let's see if we can explain this behavior. First of all, let me flip this back around. Because, yeah, I'm kind of like that. Red has to be in red, right? Okay, so let's see if we can explain this. Which way is the current going here? Starting here, it's going up through here. So therefore,
It's,
the current's going that direction, right?
yeah.
Now, we can't use the right-hand rule as far as a loop, right? We already know that. That's not going to be helpful. But there's this external magnet. Let's look at this external magnet. Can you see this side here's the north? That's on the far side here. Our fingers for the loop rule point in the direction of the what? Magnetic field. So let's see if we can straighten our fingers out. So our thumb's going to be pointing this way, right?
Yes.
Our fingers are that way, pointing from the North Pole to the South, or yeah, from the North Pole to the South Pole. So our thumb's this way, our fingers are that way. Let me turn it on again. So what part of our hand is pointing in the direction of the motion?
The palm.
The palm is. So it's kind of like it's being pushed that way. What's the angle between all these things? 90 degrees. So it's kind of acting kind of peculiar here. So let's see if we can apply that. This would be a new right-hand rule, right? It's not the right-hand curl rule anymore. This would be a right-hand. What's this rule telling us?
Push.
The direction of the push, the force, right? Let's see if we can apply it again when we flip these.
Oh, now your palm is
So
facing
now,
the other way.
now the current's going down this way, so our thumb's that direction. Our fingers are still that way though, right? So our thumb's down, our fingers are that way, pointing from north to south. Which way should the force be?
This way.
That way, right? So let's see if it's right. Yeah, it worked. Well, let's flip around the magnet and see if it works. Let's flip the magnet around now. So now we have north up.
Are we putting the wires back or leaving them?
No, I'm gonna leave them here for now.
Okay.
So now, our thumb is still pointing down. Our fingers point this way, right? From north to south.
So it should
And which
push
way should it move?
that way.
Should move that way, right? It did. Let's flip the wires now.
Very goes that way.
So now the current is going which direction?
Up.
Upward. Our fingers point from north to south. Which way should the wire move? This way, right?
Yep.
Let's try it.
Yay.
It works. We have a new right-hand rule.
Right hand push rule.
It's right-hand push rule. It's a right-hand force rule. Okay? So I don't know if you want to write that down somewhere. We have a right-hand curl rule. And this one is helpful for figuring out what?
2 R's are redundant.
The direction of the magnetic field.
Yeah, you can get rid of the second
R.
R in the.
Because it's for
There's
rule.
right hand rule, curl rule.
It's like
And we
18.
have a right-hand
Push.
push or force rule. Okay. So what we need to do though is in this next lab we actually need to quantify the force. What do you think, we're out of time, Marnie. What are some things that might affect how much push there is?
The current.
Current,
Magnet.
maybe the magnet strength,
Yeah, magnetic.
maybe the distance, how long the wire is. We're going to test all of those three, okay? And the way we're going to do that is we have this contraption here, and we're going to be putting this on a balance. And I'm running out of time, and we're going to have a wire that we will change the length of right here, sticking in for the magnets, in between the magnets. So there's a magnetic field. Is it attracted to the magnets?
No.
No. And when I turn on the current here, will it be attracted to the magnets?
No.
No, was it attracted to the magnet?
No.
No, it's going to be either pushed out or pulled into, right?
Which went the.
So now, it's hard to measure the force on this, but if I have this on a scale, think about Newton's third law. If this has a force this direction, this is going to feel force,
Downward.
and therefore it's going to weigh more.